session, the titled Advanced Trends in Efficient Inference. In this session, we will have 3 regular papers and 1 late-breaking paper. So for regular papers, the presentation time is 25 minutes. So 20 minutes presentation plus 5 minutes Q&A maybe. Okay, let me introduce the first speaker. First speaker is Harsh Sharma. Harsh is currently a PhD candidate in Washington State University. He did his undergrad from NSIT Delhi University in Delhi, India. Harsh has worked as a machine learning engineer for AR applications before starting his PhD. Goal of his research is to develop principled AI-driven design paradigms in huge search spaces for efficient chip design built toward high-impact applications. Okay, let's welcome speaker.
Hi, am I audible? Good afternoon, everyone. My name is Harsh, and with my advisor and collaborators from Washington State University, Topol Labs, and University of Wisconsin-Madison, would like to present our work called Florets for Chiplets, which is a data flow-aware, high-performance, and energy-efficient network-on-interposer for CNN inference tasks. Firstly, I would like to lay down an agenda for this presentation. I would go over the motivation and related work. Then I'll talk about this workload-aware network-on-interposer design, where we'll talk about the space-filling curve for this network-on-interposer design, and talk about the Floret architecture, which is within which we talk about the hardware-software co-design, which is the neural layer to chiplet mapping, and the overall Floret architecture design. Then we go over the explainability idea of why this works better by showing the NOI, the network-on-interposers, router and link configuration, the performance analysis, and finally, we conclude the presentation with the vision forward. So as it has been highlighted in multiple technology roadmap that it is very evident that industry is moving towards smaller nodes, and hence the yield is decreasing, where the byproduct is manufacturing of a larger chip is not economical. As you can see over here, in die, a wafer of about 3 centimeter, we have 10 millimeter square die with about 33% yield, which means only 1 out of 3 chips are going to be fully functional. However, there have been some innovations within 3D stacking, but it gives some of the issues which are currently faced, like the temperature hotspot and additional dollar cost around the routers when we have these 3D layers shown in purple, which are called as the keep out region. So why chiplet in the first place? So we'll talk about what is chiplet. So we take this bigger chip and we divide it into smaller dies, which are fabricated on a single wafer. As you see over here in this figure, we have white chiplets. Each of them have their own router, and they're connected by these links, which are double arrowed links. So it's a compact scale out implementation, and they're connected through this network, the NOI that I was talking about earlier. However, in this case, because the yield improves, because the defects are amortized on a smaller die, so it is an economical manufacturing process, but it has issues now that the chiplets are physically far apart. You can see the scalable communication due to this larger physical distance becomes an issue. There might be thermal issues within the technology node that we're using and defects. But here, we should kind of think about how industry is approaching this paradigm shift. So the biggest issue of all, the challenge, is the communication, where it is highlighted here, one of the toy example for chiplet, where system scalability and fabrication costs actually hinders the widespread adoption, where the obvious reasons are poor technology scaling as the wire length increases. We have larger physical distance, as we can see by these pink nodes, and it's overall a power constrained environment. However, an efficient NOI, the network-on-interposer, can solve this problem, but we need to have this idea baked in, which is performance should not be compromised. And we should maximize energy saving as the system size scales, because we expect the number of chiplets are going to increase. Additionally, NOI consumes 80% of the total area of this chiplet-based system, and energy consumption is the bottleneck of the NOI. So there's an inherent need of scalable architectures. It's immediately important we address that. So there have been related work in this field, starting with Pascal Vivet's work called Intact, which is a 96 chiplet system which put the baseline for lower latency interconnects. Next was by Stanford and NVIDIA joint contribution called Simba. Simba is a 36 chiplet DL application system, which was introducing tiling optimization in the first place, where they were creating this application specific NOI on the 2D mesh. Then there's a family of topologies which are misaligned called kite, where we have skip connections being introduced like the purple or the orange one, but is primarily a torus-based architecture. And then there's SIAM, which was one of the cases paper in 2021. It's a scalable evaluation framework in 2.5D system. It assumes a 2D mesh on the NOI. None of these work are DL workload aware. So we don't know what we might be expecting as the time goes on. There might be an imaginary net. So to solve that problem, we had an application-specific architecture in last year cases called SWAP, which assumes an irregular NOI, where the NOI placement and the core placement depends on what is the traffic. But the issue is, in case of concurrent CNN tasks, which are at data center scale, none of the previous workloads actually solve that problem. But Floret effectively, by its inherent NOI that we'll see later in a few slides, kind of tackles that problem. So our novel contributions, we are the first workload-aware NOI for this data center scale workload that you might expect in Google, Facebook, and beyond. We evaluate up to 8.8 billion parameters, and we use RERAM-based PIM architecture. Here, I would like to make it clear that this NOI architecture is agnostic, and any of the technology node could have been used. We use space-filling curve-based NOI that I'll talk about why space-filling curve and what they are. We enhance the performance and lower the energy consumption, and we have this inherently versatile NOI for deep learning workloads, which are beyond CNNs. We use a hardware-software co-design, kind of good for this track, and also we lower the fabrication cost that we talk about later. So it's a critical step towards making chiplet-based mini ecosystem design more accessible. So let's talk about this workload-aware NOI and space-filling curve. So first, I would like to bring out a similarity to a human brain, a neuromorphic similarity. Most of you might be aware that we have multiple different parts in our brain which are supposedly doing different tasks. They might be happening concurrently and within one lobe, for example, the frontal lobe, which is for visual recognition, or the occipital, which is for spatial recognition or depth analysis, that might be working concurrently. So we have multiple tasks which are happening, which might have within serial execution. And we have concurrent execution of tasks based on what type it is. So the space filling curve, as an idea, represents a class of algorithms which basically maps something in 2D using a one-dimensional space. It generates a locality preserving data structure, which will make more sense once we look at the physical realization in the next slide. And SFC traverses the area with no closed loops. So kind of looking at this architecture as an example, we have a neuromorphic idea kind of baked in as a toy example, Floret being on top of brain. So let's look at the physical realization that I was talking about. Here you can see that we have a hierarchical top level network. And there are multiple SFCs of different color, from purple, red, whatever. We have links between neighboring chiplet along this contiguous SFC path. Then we have inter-SFC link, which we call as the top level network. And then we have intra-SFC. So there are two parts where this problem of actually accelerating data center scale inference of CNNs, we have this one common property that no matter what the activations go from Li to Li plus 1. We might have skip connections that we'll actually address later in the next few slides, and we maintain a contiguity along the NOI path. Our design considers a head and a tail. So a head of a SFC is where it starts, and the tail is where it actually ends. And then we have a trade-off that, okay, what are the number of SFCs and how long each of the SFC is? And we have this hierarchical structure. You can see it could easily be like a traveling salesman problem, where you start at one end and you have to end back at the same place. So we kind of solve it with engineering principles of symmetry and decomposition, but there's a trade-off between what are the sizes. So the common property that I was highlighting as have been in a lot of papers for DenseNet and CNNs, we have an input image, convolution layer pooling. We always have this activations from Li to Li plus 1, which is primary. Our experimental results have included DenseNet, ResNets in multiple different scenarios. And maintaining this contiguity on NOI actually solves the problem very effectively. So here I can give an example to last year's cases paper, which is SWAP, where obviously when we are mapping something which is runtime, we were not optimized for it before. So here we can see that we have unconnected islands which are created. So the left one is one example of SWAP, and the right one is the Floret architecture that I'll go over one by one, making the similarity and the differences. So in case of SWAP, we have unconnected islands. The reason is we are trying to map greedily. We want to have smallest possible path between each of these communicating chiplets. In Floret, we map the layers according to the Hamiltonian path, which is along the SFC, like starting from H1, go to T1, going on H2 to T2, and we come back to the same H1 when we proceed along this path. The benefit is, in case if the workload is much bigger than what our system can actually serve, we will basically be on the chiplet that is going to be the next available resource. So the chiplet resource becomes available as new layer allocation starts. So during the mapping, if we reach one of the tail, we have more than one option. So in case if there's inherent redundancy in the system, where if the yellow link is broken and we cannot use the section of chiplet, so we have introduced this inherent redundancy that we get as a byproduct in the system, which gives it that mapping benefits. So how do we find the optimal number of SFC? The idea is that we reduce the average number of hops between tail of one SFC and the head of the other SFC. The idea is that once we are on a given tail, we want to go reach the next possible head in shortest amount of time. The H average is calculated for all of these head-tail pair. And multiple SFCs are introducing the redundancy, but if one of the SFC is longer, then might be the resource might be wasted. So we have this trade-off that what should be the size and what should be the number of SFC. Another benefit is the top level network should not be big enough, because that's where we have the issues coming in. So the optimal number of SFC when we analyze for 36, 64, 81, and 100 chiplet system in this work, we lie between 4 to 6. Now, one question might be that one of the SFC could have been longer and other could be shorter. So we do like a simpler analysis on 36 chiplet system where we see equal SFC actually performs better because we have more homogeneous design. So latency comparison is shown where equal length actually improves when compared to an unequal length SFC within the system, which is like a basis for creating these Floret architecture that we'll see. Again, the balance between the size, psi of each of the SFC and the number of SFCs. So as we can already see that because we have this Floret architecture where we are just connecting one of the chiplet to one of its predecessor and the next one, we have the smaller router ports, kind of the explainability idea of why this works better. We can see all the other architecture, Kite, SIAM, Swap, and Floret, where we have the number of routers being smaller. So the peak of Floret in router port configuration move towards the left, where we have mostly 2 routers, the idea, and 3 in case of inter-SFC, so we can give that redundancy. But that is not just enough. We also need to look at how many links are there and what are the length of these links, because it is crucial to consider what is the link length between these routers. Now we are physically far apart. So Swap has smaller routers, but not all links are necessarily single hop because we have these bypass kind of. So we also introduce some longer links in case of Swap, which could be 4 or 5 hops. Floret mainly consists of routers with fewer ports, and all the links are single hop that we show in the figure. So going on the fabrication cost aspect of it, the fabrication cost is a function of number of routers and the link, where the area of the NOI, which is going to be between area of the router and area of these links, becomes the part. In SFC, there are 2 parts, the hierarchical top level network, and we have the inter-SFC and the intra, which are the 2 parts. So when we consider that, we can see the area finally, when we take a relative percentage, how much is the improvement, basically boils down between the difference of 2 NOI areas. So because we saw that figure about having smaller router ports, so our fabrication cost improves 80%, 60, and 49% with respect to counterparts, which are Kite, SIAM, and Swap for 36 chiplet system. And this improvement actually increases because as the system size scales, Floret is a linear, whereas other cases are not. We'll look into it later again when we talk about the conclusion. So let's talk about the performance analysis and look at where are these concurrent CNNs these are used. So real-time video analytics is a good example where you might have to do maybe use a ResNet 50 where you're doing a classification, and at the same time you need a segmentation model. So they're running concurrently within one single system. Other scenario might be cloud computing, which are used in the ensemble of models in case of Facebook and Google Photos, whoever has used, you have geotagging and image tagging where multiple CNNs are used together. So they're being done concurrently. One image is being used for one part of the ResNet, other is for DenseNet for say geotagging. The third example might be on edge computing where multiple CNNs can actually process locally. So as we go by, we don't need to send out a sensitive data to the cloud. So we consider these data sets to emulate the data center scale that we are talking about. So here you can see right from ResNets on CFAR 100 starting from 1 million so parameters densenet VGG, up till we go up to ResNet as big as 890 parameters. This is just one single data set, but we actually emulate the whole scenario with taking the ensemble where they're running concurrently, as you can see in the biggest 8.8 billion parameter. If you remember these NNs, they just represent what they were. So we have 5 ResNet followed by some VGGs, multiple dense nets. We use NVIDIA GRS parameter to implement all considered NOI to have this equivalent scenario. So there's a fair comparison. So the only difference is the network on interposer and also the mapping that we are doing. So here, let's look at the activation flow. Say, for example, I start mapping here at the red part. I continue at this point. I have an option. Maybe I can jump here if there was already a resource here, or we continue along this path. Using this as the bare bones structure, we ensure that if the incoming CNN requirement, some imaginary net with, I don't know, 1,000 layers might be introduced, where we might have much more higher compute requirements that we have, we would be connecting. So if the layer first is mapped here and layer 15 is mapped on the last SFC after coming back, the next one will be getting available on the red part. So we always ensure that continuity, which we need when we are on the longer workload, and shorter, it works effectively due to the Li to Li plus 1. I have a visualization kind of showing what is the difference between the improved performance. So this is SIAM standard in NVIDIA, and also this is Floret, where you can see the less links. Let's look at power versus time of execution. For same workload, no pruning, no quantization, both of them have same traffic. You can see as the power consumption is higher in case of swap as the time of execution goes by. For a workload 7 with over 8.8 billion parameters, where you can see Floret is already done, where SIAM is still running the exact same workload. So we save 1.8 times latency when compared to 2D mesh. And this area under the curve, as you can see, it's much lower, actually captures the energy consumption. So let's look at what were the actual numbers. So in case of 36 chiplet system, average performance with one example called Kite is 27%. We go up to 51, 82, and about 100% improvement due to this contiguity, which was not in the other scenarios, and having this hardware software co-design where we map along this software path. So because being data flow aware, we know about the data flow, what we might be expecting. Floret prioritizes the performance, whereas we are able to address these skip connections as we have considered because they flow through the NOI. Let's look at the energy savings, which is a byproduct of lower power consumption having smaller routers, where Floret enables significant energy savings with about 2.7 times with respect to Kite. And with respect to swap, the last year cases paper, about 1.6. Having smaller routers with reduced number of links actually leads to this energy saving that we are seeing. So the fabrication cost quantification, we know NOI area is the function. We have smaller routers, smaller associated ports, and fewer links, and which is complementing the performance and energy. So I have this one figure over here for a 100 chiplet architecture, which is trying to capture the latency and the energy consumption for workload running on 100 chiplet system, where you can see the improvement is about 76% in latency, 50% in energy. The size of dot actually shows the power consumption. And the last part, because we have embodied carbon emission, which becomes a bigger problem as we go on the data center scale. This is obviously improving because now we have smaller NOI area. So as the system size scales, that becomes an important parameter to consider as the size increases. So we have reduced carbon emission on that front. So in conclusion, in the vision forward right now, we just considered homogeneous chiplets. We could have individual SFCs with this similar hierarchical top level architecture where we have different types of CPU, GPU, DRAM, and accelerators. And this scales better as we go into 3D due to this linear dependency. And there could be potential generalization as we have seen in these concurrent tasks on DL workloads. One example that I would give due to this contiguity and this heterogeneous, we can actually accelerate these newer multimodal architecture. For example, the feed-forward layer, which is within the transformer model, has a similar Li to Li plus 1 nature, where that transformer model's feed-forward could effectively just be an SFC. So in summary, designing data center scale chiplet system poses significant communication challenges, obviously from the physical data, the physical distance between these chiplets. Floret is first workload aware NOI architecture for these data center scale deep learning workloads. The benefits are, higher performance, the reduced energy consumption. We lower the fabrication cost due to having smaller routers, and we also lower the carbon footprint as the system size scales. We see that improvement. Thank you. that was all for my presentation.
Okay, and now we have time for Q&A. So any questions? Okay.
This is working. One quick question regarding the performance and energy comparison. Correct me if I'm wrong, but I can basically overlay a space filling curve on top of a mesh architecture, right?
Yes.
In which case the performance should be similar.
Right. In case of mesh, there's one dependency, because if we are doing the hardware software co-design, the bigger issue becomes the power consumption. So in case of mesh, we can still have, this is like an embedding. So on Kite also, which is one of the architecture, so where we can also create a space filling curve.
Yeah.
So it is agnostic to whatever. So
the performance should be similar in that case. Is that correct? Or do you expect a difference?
Yes, it depends on what kind of mapping are we doing. So in case of, if we use a greedy mapping where we are not being aware, so that is going to be the difference.
But then also the second part for the energy, where do the benefits come from? Just from finishing earlier and hence leaking less? Or is it
the benefit is in two parts, because we have smaller router ports. The power consumption of each of this communication actually reduces. So while the time they're running equally, so we might have to wait longer if we are not doing this hardware software co-design where we map along this contiguous path that we actually created. So that's where we get the benefit. So the same workload would take longer time because we are waiting while it is getting inferenced.
Okay, thanks.
Okay.
I just want one clarification. You use the word explainability. What does that mean basically in this context?
So here, just this idea, the Floret architecture, the reason why it's performing better, it comes in because of the reason why it's performing better when compared. The explainability, just the word as in like why it performs better, not into the, yeah.
Very excellent work. So I think the methodology you apply to NOI can be also used for NOC design. So what are the new challenges that should be solved for NOI design?
I can give you an example. So we can imagine this space filling curve in a 3D IC setup also, where we have this NOC design where the traveling would depend on, you have X, Y, and Z axis where you can probably travel. So the size of the search space becomes increased. So that is one possible scenario where we can do the space filling curve architecture.
You mentioned workload aware, right? So you are designing a different architecture for each mix of workloads?
So this is one fixed architecture. So the workload awareness, the word comes in from this contiguity that we are maintaining due to the Li to Li+1 nature. So it is agnostic to whatever CNN we might use, because all of the CNNs have that Li to Li+1 primarily. The skip connections travel through this NOI.
So you optimize based on, not on a fixed set of
yes,
workloads.
The architecture is fixed to what we were.
What is the workload model then? Like,
so workloads vary from, if I go to one of the previous slides, I can show this figure as an example where each of these are mix of different workloads, which were like 16 ResNet, 34 are running, after which the concurrency is VGG 16 and so on. So this is one example where we have.
So you don't optimize for each of this set of workloads?
No, the architecture is fixed. We run these on multiple different to see how robust our consideration is when we have different set of CNN tasks coming in. So it's fixed NOI, one single architecture for one system size.
So in your experiments, actually, you are assuming that all applications are
on one single architecture
at once, and you just measure the finish time of that?